a triangle has two sides. That's not really true because a triangle has three sides, but two of these sides are A and B, and the angle between the two sides is theta. Then we want to determine the value of theta such that the area of the triangle will be a maximum. So let us start with a diagram. So there's A, there's B, and there's theta. And then there's some third side, which shall remain unnamed for it's in witness protection. So. And we want to find the area of a triangle, right? So we know that the area of a triangle is 1/2 base height. Which means I really should have put the B down there, but never mind. So we need a height. So we drop a perpendicular, and we'll call this the height, H. And then we'll say stuff like, oh, well, really we want to get this, since it's theta, right, we're looking for theta, so we want an expression for area in terms of theta, such that we can find its derivative, and besides this trig derivative, right? Such that we can find its derivative, and then find the maximum area, right? Okay, so what do we know here? Well, we know that sine theta is equal to opposite over hypotenuse, which is h over b, which leads to h being equal to b sine theta. So if we do that, you see, notice we're going to have that 1/2 and a b and a b sine theta. And the b is a constant, right? B is a constant, right? B is not changing. We're not changing the b. We want to change the theta, right? We've got these two sides of some length, A and B. They're not changing. We're going to change the angle between them such that we get a triangle whose area is a maximum. So, area. Oh, but wait a sec. Don't do that. Look, if we get the height, right, the highest height is going to give us the greatest area, right? Because again, the B is fixed. So let's just take the height and maximize it, right? So H is equal to B sine theta. If we maximize H, then we maximize A, right? If you got the highest height, then you're going to have the greatest area. See, the area only depends upon this fixed base, which is really the A, right, and the height. Okay, so let's do dH by d theta, which, and remember, b is a constant, right? So it's like, just think of it as like 5 sine theta or something. So you're just going to write down the b and then a cos theta, being the derivative of sine. So we know that we would have a maximum when b cos theta is 0, right? So we will get a max or a min, right? It could be the minimum when, at which point I guess we should say something about theta, right? So I mean theta can go from 0 to pi over 2. Feel free to use degrees if you so desire. It's not really any, huge deal here. So between 0 and oh no, well, it'd be pi, right? Pi. So theta could go from 0 to 180. Those would be the extremes, right? Now, if theta were 0, we'd have an area of 0 because you wouldn't really have much of it. If theta were 180, again, okay, you couldn't make a triangle. So. But, we need to examine extremes. Once we found this, we need to say, well, here's the extremes, right? Your theta can go between here, and at 0, yeah, you don't have, and at pi, you don't have, so. All right, which means that cos theta is equal to 0, which means that theta is pi over 2 or 3 pi over 2.
It has to be 0. You can cancel it. You can't take that.
Can you street pi over 2?
The domain's 0 to
Pi, right. Okay. So, yeah. Good pickup there. All right, so either theta is 0 or it's pi over 2 or it's pi. So when theta is 0, b sine theta will be 0 because sine theta is 0. When theta is pi, sine theta is 0. So theta is pi over 2, which makes b or sine theta equal to 1, so that h is equal to b. Okay. So really, it just means that it's got to be a right-angled triangle, right? Value of theta that maximizes the area. Okay. So having examined, so if theta equals 0, then h is 0. If theta is pi, h is 0. So the what did the question say? Determine the angle. All right, there. Easy. Okay. I'll leave it here. I'll pause. There's no point. Determine the maximum perimeter of a right triangle with hypotenuse 20 centimeters. Okay, so let's draw a diagram. It's got a right triangle. This is 20. There's some angle there, theta. We know that theta will be between 0 and pi over 2. Right? I mean, those would be the extremes. Actually, just in either end from them. Those would be the extremes. So, let me shift that down a bit. This side here is 20 sine theta. And this side here is 20 cos theta. And so the perimeter is 20 plus 20 sine theta plus 20 cos theta. So, I'm thinking of factoring out the 20, but I guess we don't need to do that. So P prime, so the derivative of 20 is 0. The derivative of 20 sine theta is 20 cos theta. And the derivative of 20 cos theta is minus 20 sine theta. So now we could factor out the 20 if we want. So we want P prime equal to 0. And we'll factor out 20, and then we'll divide both sides by 20, and let's end up with sine theta equals cos theta. And then divide both sides by cos theta, and get tan theta equals 1. Right? So we divided out the 20, we've got sine theta has to be equal to cos theta, that's how they're going to be 0. Divide both sides by cosine theta, and you get sine over cos, which is tan theta. And the right side is cos over cos, which is 1. So tan theta is 1. And the only value that's going to work there is if theta is pi over 4. Are we supposed to find the angle? What are we supposed to find? Oh, we're supposed to find the maximum, right? Okay, so theta oh, look, it actually works today. It's amazing. Is that like 1 out of 5 days? Once a week. works as it should. So theta is pi over 4 or 45 degrees. Now let's just stick with so P so if theta were 0, because we have to examine the extremes, right? So if theta were 0, then we've got 20, the sine of 0 is 0, so this goes away, and the cos of 0 is 1. So we get 20 plus 20, which is 40. If theta were pi over 2, then the sine of pi over 2 is 1. So we get 20 plus 20, and the cos of pi over 2 is 0. So 20 plus 20 is also 40. And if theta were pi over 4, then we get 20 plus 20 sine pi over 4 plus 20 cos pi over 4, which is 20 plus 20, what do we got, root 2 over 2, that's 10, plus 20, we got root 2 over 2, so that's a 10. We get 20 plus 20 root 2. Well, root 2 is bigger than 1, so that makes this bigger than 20, which makes this thing bigger than 40, and so that's your answer, right? It's larger than the other two values, which both would be 40. So there we have a max. Pause. Determine the dimensions of the rectangle of maximum area that can be inscribed in a circle of radius A centimeters. Okay, so there's a circle, yes. What? Oh yeah, it's been up there for a long time.
Mr. Hanover just jumps up, grabs it.
Ask your doctor if tetrahedral.
But you can't do it.
That's at least it's math related.
What was it?
It's just a note.
Awesome. Are we recording?
Yeah, we are.
Okay. Is it not something you could say? Camera?
No, I just said ask your doctor if tetrahedron is right for you. I know, right? So what are you going to do?
Probably paint the picture.
All right, so let's inscribe a rectangle inside a circle, and then let's draw the diagonal, which will go through the center of the circle, right? And we've got a radius of A. But really, why not use R? Why not use R? I'm going to use R. There, the A has been changed to R. Edit your papers accordingly. So this will be 2R, and let's call this L, and let's call this W. Right? So we've got a length and a width, and then we've got the diagonal, which is 2 radii. And we know that L has to be between 0 and 2R, as does W. Right. So we can basically have no width and then just the rectangle, which will really just be a line equal to 2R, but that area is not going to be all that big, as in 0. Or we could have it running this way, okay, where we have W is 0 and we've got the L, okay, but we know it's somewhere in between, right? Somewhere in between. So area is length times width. And what's our relationship? Well, okay, we've got a right-angled triangle here, right? So we know that L squared plus W squared is equal to 2R, quantity squared. Right? Because we need to get this into one variable. Right? And I like L for some reason. So L squared, plus W squared is equal to 4R squared. So W squared is 4R squared minus L squared, and W is the square root of that expression, right? Okay, so now we have W in terms of L. So now we can go back to our area expression and write that it's length times width, but width is the square root of 4R squared minus L squared. And now we can take the derivative. Okay, now remember, R is fixed, right? I mean, R is a constant, some constant. It's L and W that we're interested in. So A prime, or dA by dL, or we're taking the derivative with respect to L, is, what do we get? How do we do this again? It's use like L times the derivative of this, which would be 1/2 of 4R squared minus L squared to the negative 1/2 time, I have space here.
I did too.
Okay, got some space here. All right, so it's what else do we have? We've got like a negative 2L in here or something. Blah blah blah. Negative 2L plus the square root of, well, let's just write this as 4R squared minus L squared to the 1/2.
Don't you have to multiply by 8R?
No, because R is a constant.
Uh,
Okay. Remember, R is constant, so 4R squared is just a number like 5 or whatever, right? So we're not taking a derivative. Not with respect to R, just with respect to L. Okay, so what's that give us? All right, so we got the half, negative 2L, so that's going to be a minus L squared. All right, so let's do this. The square root of 4R squared minus L squared, that's this guy, minus L squared over the square root of 4R squared minus L squared. Okay, so there's your expression for the derivative of area.
You just give us a rundown.
Okay, so L squared. Half, 2, 1, minus. Minus L squared, this down here. This, that's that. So this is that, and that is this. Yeah, it's like the end of that. You ever watch a Louis C.K. thing to the end where this is this and that is that? Okay, so we're going to set that equal to 0, which means we're going to move the thing that's negative over to the other side. Miracle of miracles, since these guys are the same, right? When I go to cross multiply and when I go to multiply by this, kind of neat, right? So L squared is just going to be equal to 4R squared minus L squared. Right? See how the roots radically disappear? So 2L squared is 4R squared. So L squared is 2R squared. And L is root 2R. Right? Where the R is not under the radical sign. Which usually takes us right up here where W is the square root of 4R squared minus root 2R squared minus 2R squared which is 2r squared, or root 2r. So look, L and W are the same. So it's a square. Yeah. Rectangle maximum area is always a square,
Probably could have guessed.
whether it's inscribed in a circle or not. You should know this from, I don't know, 20-1. Yeah, little logic doesn't hurt. So if I want to make a rectangle, it's got the biggest area. It turns out it's a square. Now, they're either that or they're 0 and 2r, right? Now, we know that this area will give, if L is 0, we'll get an area of 0, and if it's 2r, we'll get an area of 0. So here we are, and that's it. So the dimensions are root 2r by root 2r. Are there units on it? There's no, it wasn't units, right? It's just r's. So, was it centimeters? I can't fix that. There you go. Okay, one or two more? Two more. Two more. I'm going to change this. I'm going to change the numbers. So I'm going to make this into a 10. Make this into a 10. And the biggest change is making that into a 10. Otherwise, it just turns into another rectangle. And we don't want that. Okay, so imagine, think of that as a gutter, right? You've seen gutters. So gutters are trapezoidal in shape. So we've got like 30 centimeters of sheet metal, and we're going to bend it into a gutter, so it'll be like 10, 10, and then 10. And the question is, so what angle, as shown there, do we use to get the maximum area of the trapezoid, right? I mean, obviously you want this thing, which would also maximize the volume. If it were a gutter, that would be the maximum volume that it could carry. And you're going to want that. You got water coming off the roof. You want to maximize the volume of the, you can make it like really long with not much of a lip, but then it wouldn't hold much water, and if it's raining hard, it's just going to be spilling all over the place. So we want to maximize this. Okay, so area of a trapezoid is 1/2 of a plus b times h, where a and b are the lengths of the parallel sides, and h is the distance between them. Okay, so you know that, right? So this would be like A, this would be B, this is B, and this is H. Now H is 10 sine theta, right? I mean, theta is opposite over hypotenuse, so sine theta is H over 10, so H is equal to 10 sine theta. A is equal to 10, and B, well, this here distance is 10, and this here distance is 10 cos theta. Right? Kind of the same reasoning, right? I mean, so it's the same as this distance down here, right? So there's theta, this is adjacent, that's hypotenuse. Cos theta is this distance over 10, so this distance is 10 cos theta. And then as is this. So B is equal to 10 plus 10 cos theta plus another 10 cos theta. So B is 10 plus 20 cos theta. All right, so what have we got? Well, we got a number, 10, we got a 10 sine theta and a 10 plus 20 cos theta. So we can now express area in terms of the angle, right? It's the angle that we're interested in, right? So that's the thing. We have to express area in terms of the angle. Okay, so let's just think of this as h over 2. Okay, so h, so we've got 10 sine theta over 2 times a, which is 10, plus b, which is 10 plus 20 cos theta. So let's go with 5 5 sine theta, and 20 plus 20 cos theta. So one reason I changed the 10s to, or the 5s to 10s was because I knew I had to divide the height by, and you know, dividing 10 by 2, nice number, not 5 halves, no fraction. All right, so what are we going to do? We'll consult notes. So if we're going to take the derivative of this, why not just multiply this out? So, right, so we got something plus something, and then we just do the derivative of this plus the derivative of that, which is easier than making it a product, and right? Okay, so we got 100 sine theta plus 100 sine theta cos theta. Now at this point you say, wait a sec, I've seen that sine theta cos theta thing before, right? And I know that 100 sine theta cos theta can be written as 50 times 2 sine theta cos theta, which is 50 times sine 2 theta. Right? So let's replace the 100 sine theta cos theta with a 50 sine 2 theta. Because that'll simplify things again, right? I mean, if I take the derivative of 100 sine theta cos theta, we got to work through our product rule, right? If I take the derivative of 50 sine 2 theta, then we got to do a little bit of chain rule, but hey, it's only the number 2. Brought to you by the letter A and the number 2. Okay, so A prime is, so the derivative of sine theta is, and the derivative, so we got 50 times derivative of sine theta is, and the derivative of 2 theta is 2. Right? Easy. So we got 100 cos theta plus 100 times cos 2 theta. To which you, of course, immediately say, wait a sec, the cosine of 2 theta is 2 cos squared theta minus 1. And if I were to put that in here as 2 cos squared theta minus 1, then I'd end up with a cos squared theta and a cos theta and a number, or a quadratic in cos theta, which hopefully factors and then solves quite easily, right? So we're going to do that. So cos 2 theta, so here we'll just scrap paper. So cos 2 theta, remember, is 2 cos squared theta minus 1. So let's go do that. And what do we do? Well, we're going to set that equal to 0, right? And probably extend the page, yes. To extend the page. Okay, so 0 is equal to, and then let's write this so it actually looks quadratic. 200 cos squared theta plus 100 cos theta minus 100. And we can take 100 out of there, right? We get 2 cos squared theta plus cos theta minus 1. So we're going to have a 2 cos theta and a cos theta. Two numbers multiply to 1. 1 is positive, 1 is negative. The numbers are 1 and 1. Now, if you're going to mess up, you're going to put them in the wrong place. So this plus, so I'm going to go plus 1 minus 1. Every time you factor, multiply it out, right? 2 cos squared theta plus 2 cos theta minus 1 cos theta is plus 1 cos theta minus 1. You're not going to get these numbers wrong. You're not going to get these wrong, but you might get the signs wrong, in which case then it all, just becomes a mess for you, right? Because now it doesn't solve properly. So anytime you factor, quickly FOIL it out. Just make sure that your signs are in the right place. Okay? And even if you're factoring like a difference of cubes, right, which I always do kind of as I sort of know what this looks like, but then I'm going to multiply it out, make sure that it's the correct, that I get the x cubed and then I get a plus this squared minus this squared. Okay? So just double check. All right, so 2 cos theta minus 1 is equal to 0, or cos theta plus 1 is equal to 0, so cos theta is a half. Is there any restriction on theta? What is this thing? Oh, well, so theta is really between 0 and pi by 2, technically, right? Or, well, between 0 and pi, I guess, right? You can lay it flat this way, or you can fold it over flat that way. Now, if it's 0, there's no area. It's just a flat sheet of metal, and if it's pi, then it's all the way in, so that it's also just a flat sheet of metal. It's not going to hold much water, so the areas will be 0. So maybe we'll write that down somewhere. Okay, just because we got to now work these guys out. So if cos theta is a half, then what's theta? Pi over 3, right. And the other positive value being quadrant 4, so that's too big, right? So we don't want that. And here, cos theta will equal -1. So then theta is pi. All right, so it's either 0 or pi over 3 or pi. That's our extreme. And it's definitely not 0 and it's definitely not pi, so it's pi over 3. Now, did we have to find, what did it actually ask us to find? Just the angle? Okay, so we're done. Okay. Now, I mean, you could work it out, so we could go back up here. We could go back to here, substitute in, theta is 0, which makes this 0, which makes that 0. We could put in theta is pi, which makes that 0, and we'd have a 20, and this would be a 1, so it'd be 5 times, it'd be 100. And then we've got the pi over 3, and so technically we should put that in and just make sure that it's over 100, right? Which it is. But I'll leave that as an exercise for you. That way we finish off and we're done. Okay, let's finish this unit. The ladder in the hallway problem. The famous ladder in the hallway problem.
Classic.
It's true, it's a famous problem. So we're walking down the hall, and the hall bends, right? And you're in a wide hallway, or there's an 4-foot wide hallway meeting an 8-foot wide hallway. So let's draw a diagram. So here's the hall. This is 4 feet. This is 8 feet. And you're going to turn the corner with the ladder. Wait, I should probably extend this out a bit.
Not even
So there's the ladder, right? I mean, you got to make it through here, so it's got to turn. Okay. So it's an infinitely thin ladder that doesn't bend. It's made out of spider silk or something. It's like really strong. That stuff is strong. It's like gecko sticky stuff. So geckos use to stick their feet to things. That stuff's strong. And yet it peels away easily, right? That's how they can walk around. Nature's come up with a lot of solutions to things. So there's L, which will be the length of the ladder. And let's call this length here A. And let's call this length here B. So there's going to be some angle.
What did it say on the top?
What's what?
It's like L and then...
So this is L. So the length of the ladder is L, and I've split that up into A and B. Okay, so we've got these two lengths. And I'm going to put put a red theta in here. So that's theta, that's the parallel lines, transversal, that's we could draw another parallel line there. So we've got these three thetas, they're all the same angles, right? So what we're going to do is come up with an expression for B in terms of theta and come up with an expression for A in terms of theta, right? So this distance is 4, so there's B. This is the hypotenuse of this triangle. So we've got 4 over B, so sine theta is equal to 4 over B, which means that B is 4 over sine theta. So B is 4 times the cosecant of theta. And we've got A. And so this distance is 8. This A is the hypotenuse, right? And we've got the 8, so we've got adjacent and hypotenuse, so that cos theta is 8 over A. So A, clean that up, 8 over A. So that A is equal to 8 over cosine of theta, or A is equal to 8 times the secant of theta. And so L is equal to A plus B, right? It's 4 times the cosecant of theta plus 8 times the secant of theta. So L is equal to A plus B, which is 8 times the secant of theta plus 4 times the cosecant of theta. So it's all nicely expressed in terms of the angle theta, right? So now we're going to do L prime. And with our handy formula sheet in hand, because who remembers the derivative of secant theta, right? All right, so what do we got? We got 8 secant theta tan theta minus 4 cosecant theta cotan theta. And we're going to set that equal to 0, right? Now we're going to say, well, you know what, okay, what's cosecant is 1 over sine. So if I were to multiply both sides by sine theta, that would get rid of this guy here. And if I also at the same time multiply by tan theta, that would get rid of this here. So I can just turn this into a number by multiplying by sine theta, tan theta, right? Just the two reciprocals of these guys. So we're going to do that, right? That's where the trickery comes in, or the insight. So multiply both sides by sine theta, tan theta, for reasons as stated immediately previous to this. So we get 0 equals 8. Now, secant is 1 over cos. So when I multiply the secant by a sine, I'm going to get tan theta. And when I multiply what is now tan squared theta by tan theta, I'm going to get tan cubed theta. So 8 times tan cubed theta minus 4. Okay. It worked out even better than we could have hoped, because the secant theta tan theta became a single trig expression, right? Just tan cubed theta. It would be easy to solve because we're just going to cube root. And by easy, I mean, well, you know, relatively speaking. All right, so what are we going to say here? Let's say 8 tan cubed theta is equal to 4. Right, so all I've done, I moved the 4 over to the left, and then I switch sides, flip the sides. So tan cubed theta is 1/2. And tan theta is the cube root of 1/2, or 1 over cube root 2. So at this point, we're going to say, well, okay, tan theta is y over x, so y is 1, and x is the cube root of 2. Because if I want to find the length of the ladder, then I need to know what secant theta and cosecant theta is. All right? So we've got 2/3 of the puzzle here, right? We've got y, we've got x, we need r. R is the square root of x squared plus y squared. R is the square root of the cube root of 2 squared plus 1 squared. So R, okay, so the cube root of 2 squared is 2 to the 2/3, right? 2 to the 2/3. Plus 1. Okay, so now we got x, cube root of 2. We've got r, the square root of 2 to the 2/3 plus 1, and we've got y. Okay, and we've got L. So let's go over here. So L is equal to 8 times the secant of theta plus 4 times the cosecant of theta. Okay, so secant is 1 over cos, and cos is x over r, so secant is r over x. And r is this, and x is this. And cosecant is 1 over sine, and sine is y over r, so cosecant is r over y. So r, 2 to the 2/3 plus 1, and y is 1. So, well, 4 goes into 8 and 4. This guy is common to both terms, right? So we're going to get a 2 over the cube root of 2 plus 1. So there's the length of your ladder. And if you had a calculator, which you don't, and worked it out, it would work out to 16.6.
Textbook. I would have guessed this. Maybe like 5. Yeah,
Feet. So little over 16.6 feet you could get that ladder through. Bigger than that, smaller than that, works fine.
Why would you do this?
Why would you do that? It's a famous problem.
Why'd
Are
you
you
do this
kidding?
to us?
The ladder problem.
But the hypothesis is always largest in a square, so you can go 8 by 8 and 4 by 4.
Or just bring a hammer and destroy
Yeah.
the walls more.
Get one of those. Get an extension ladder. Yes. Oh, so I took this out as a common factor. Right. We got this and this. So what's left? So then in brackets 2, that gives me the 8. Cube root and then 8. Yes. The R from? Oh, this R. No, there's no R in the diagram. This is sine, cos, tan in terms of x, y, and r. Right? So when I knew the tangent was this, remember, tan is defined as y over x, so that's why that's x. Okay. Sine and cos, sine is y over r, cos is x over r, so I need r. X, y, and r. R squared is x squared plus y squared, right? Or r is the square root of x squared plus y squared.
No way.
I got that out of math 30-1.
Classic.
Okay? There's no r in the diagram. No R. R is simply used so that I can get the exact value of secant and cosecant,
That's what I'm saying.
right? Secant's 1 over cos, so it's R over x.
So lad.
And that's R over y.